Thank you. Episode number 2. So what I'm going to focus today is on what really was the project, the Tredurli project about, which is the fatigue of the FRP bars. I want to acknowledge again my master and PhD students from Case Western Reserve University, Charles Cope, Shudong Zhao, and Mohammed bin Najir Rahman, and then my colleagues from Italy who helped me in this project. Brief introduction, and then I will show you some of the results of the fatigue test. Also, we'll touch base on the post-fatigue response. Then I want to touch base on an important effect that we saw, and that is typically neglected, I think, by a lot of researchers, and is quite critical, I think, for the case of FRP bars. And then I will show you some of the current results that we are obtaining in the last round of tests. In conclusion, so you might remember yesterday that I showed that if you are not looking for the full behavior of a beam with FRP bars, but you're looking at really the service load when you are around for this particular bar, 0 to 30, 35 kilonewtons, really the pull-out test is enough to basically capture the behavior of the bar as the crack in the concrete opens. And so the idea in this part of the study, eventually we're running also full-scale beams, is to say, okay, let's take a look at simple tests where we can do a lot of them, let's use a pull-out test for fatigue loading to get an insight, and then we'll understand if you really need to do full-scale tests. And as we think about that, in ACI for 401122, which is the new code for design with FRP bars, there is a limit for fatigue, which has been put there since at the time. And right now, there is still not a lot, if any, research on the behavior of reinforced concrete with FRP bars. So the cap for the stress level when there is fatigue loading is 0.2 of a factor C sub E times the ultimate strength of the bar. And that's C sub E is 0.85, I believe. So again, quite low level of load. So we consider sand-coated bars first, 2 diameters, 6 and 12 millimeters.
Yeah, this is not
ran a
something my area.
As we know, there is a diameter effect, so the strength of the bars is different. We fully characterized concrete. We did also fracture test and so forth. So we had a quite good idea of the concrete. Then I showed you yesterday, basically these results with the 12 millimeters. These are the similar results with the 6 millimeter. Interesting enough, these bars in a static test, they reach a rupture of the bar, of the fibers, with 40 diameters, both of them. But for larger bars, it's a different bonded length. So I'm not sure. I think it's a matter of how the stress is transferred through the cross-section in larger bars. But anyway, we characterized fully the bars in terms of static tests. And then we started the fatigue test. So because we didn't want to have all that I showed you yesterday about the effect of the protruding part, we took the long specimen, so the 40D bonded length specimen, so that the protruding part was a minimum effect. And both for the 6 and 12 millimeter bars, we basically tested with different load ranges. And the idea was, let's go a little bit more than the 20% given by ACI, and let's also go a little bit less than the 20% of ACI to get an idea, if ACI was a safe place to be. And I should mention, for some reason, they look a little bit off in my presentation, also in there, great. For some, so for 2 specimens, actually, the bars failed. I'm going to remove these so you can see. They fail at 80,000 cycles and 100,000 cycles. And if you look at the range, in one case, you are slightly above the 20% mark, and in one other, you are slightly less than 20% mark. So just to give you an idea, these are some of the responses. I'm not going to go through each single plot, but again, the idea was our target was always either 1 million or 2 million cycles, but when we started to see change of the slope and so damage, of course, we stopped, because eventually we wanted to do some post-fatigue tests to see if we could understand a little bit more about the damage in the bond of the bar. I should mention that these 3 tests that you see here, they were run at 5 hertz. So the cycles were at 5 hertz. Then here you see some tests, different ranges, again, either a little bit above the 20% or a little bit below the 20%. For some tests, we decided to go at either 1 or 1.5 hertz. In the end, we decided to stick with 1.5 because my student was getting tired of waiting for, he wasn't getting impatient with 1 hertz. So he wanted to go a little bit faster. I said, okay, let's go to 1.5. So we basically ran again some of the same ranges, but with 1.5 hertz. These are the one I showed you before, where the 12 millimeters. These are the 6 millimeters bars, and again we try to do both 5 hertz, a little bit above the 20% in this case, and then a little bit below the 20% mark with the 1.5 hertz and 5 hertz, again to get a comparison between different different frequencies. So a quick look at the post-fatigue. So we did post-fatigue for any test for which we didn't have failure of the bars. Here I'm going to show you just some of them. So for example, this is the 12 millimeter bars between 3.8 and 30%. This one we stopped the test because we could see that the damage was quite a bit. And in fact, when we did the post-fatigue, we did not reach the 110, 120 mark, which is what we got. You see it here in red in the static test of the pull-out. So then we looked at 2 million cycles, 5 to 25 to 19%, and here we were able to get in the post-fatigue basically at where we wanted to be with the maximum load. But when we did the same cycles, 5 to 3.8 to 19% at 1.5 hertz, we stopped, and the bar failed at 70 kilonewtons, so roughly 40 kilonewtons or so below what should have been the capacity. So a change in the frequency kind of showed there was something going on in the bond. And just to give you an idea, again, this would be the static test. So this test here is exactly the red one. So again, we should have gotten there for all the post-fatigue tests. Then we did the same thing with the 6 millimeter bars. Again, you see here a couple of them, the 5 and 1.5 hertz. And here again, the bar should have failed around 37 kilonewtons because it was the same bonded length, but they both failed around 14, 15 kilonewtons. So even though the damage was not that much, both of them show that they lost somehow the capacity in the bond. A little bit to see it in a different perspective, here is a little bit of the fatigue, the frequency behavior. So this is same 12 millimeter bars, same range, 525 kilonewton, which is 3.8, 19%, so below the mark. So with 5 hertz, one could have believed that actually we were able to be okay with the ACI limit, but at 1 hertz, we were not able to get even half of the cycles. So at 1 million cycles, we had to stop because there was quite a lot of damage in the bond. Same thing for the other range. This was a little bit above the the 0.2. So again, one could argue that we were above. And same also for the 6 millimeter bar, where again, we were basically below the limit, and at 1.5 hertz, the damage was way more than the 5 hertz damage. So there is definitely a lot of frequency effect. So now we're trying to work on the modeling of this part. But in the meantime, we said, okay, we have also another bars from another manufacturers. Let's start to test also these bars. These are basically ribbed, so they're not sand coated. So these are the static tests. We test them in tension, and we started again exactly between 5 and 20% of the reduced ultimate strength. And the goal was to get to 1 million cycles, but both these two are identical specimens, failed around 150,000 cycles at 1 hertz. Now we are running right now the 5 hertz to understand if again there is an effect in the frequency, which we believe it will be there. So in conclusion, we believe that, as we're waiting that the slabs, the deck, the concrete deck are cured and ready to be tested, we believe that pull-out tests can provide some significance, some insight in the bond behavior, especially for low load level. We're not sure that the current ACI limit is actually safe or conservative. It sounds like we might need to revisit it a little bit after we have more data. And also the question is this limit okay with the typical frequencies that we see in bridges? Because between 1 and 5 hertz, we saw that much difference in the behavior. But we are also confident that these results, they seem to be also translating to other bars. So this seems to be a phenomenon that is, common to the GFRP bars. And in my opinion, to conclude, is that the resins are very rate dependent. So I believe that fatigue is a serious problem for these type of bars. But again, we'll have more probably at the next symposium when we are ready with more results. Again, thanks to the two companies who supported us with the bars, and thank you so much for listening. I was waiting.
I wanted to ask you,
yeah, so the problem is I did not put a couple of extra data here. So anything above 20%, the bars doesn't even take 50,000 cycles. So yes, we would like to do SN curves, but I think we need to do them from 20% down. Yeah, so well, if there is a Tridurley 2 and we have more money, sure. These are like pretty long tests. This has been a year just of fatigue and occupying the entire lab. Yeah, so the lab is temperature and humidity controlled. We have logs on near the machines, and we record the temperature and humidity every day. It's flat.
So that's the environmental temperature.
Yeah.
I'm thinking about temperature.
Yeah, that would be great. But if we put something there, then we change the bond. So I'm not sure if there is a way to control, but that's a good point.
Like console or something like that.
Yeah.
But there are things that I've seen, things that could
It's possible.
You
Yeah.
know, the previous thing that I did was fire to this.
Yeah.
Some point in time, I go on the road, talk, I think.
Yeah, it's possible. It's not that we didn't think about. In the end, though, in the application, it's not like there would be a way to cool off the interface. So it is possible, though, absolutely. Yeah, we can probably look into that indirectly, but I don't think we can put sensors on the interface unless we change the interface then.
Just that it shows the necessary. We did some testing of the bending of the steel, and we use infrared camera.
Yeah.
Actually, the temperature increase the quite a bit.
Yeah, yeah.
Pretty,
Oh, yeah.
pretty hot.
Yeah, yeah.
That's the fracture point.
Yeah, yeah. No, I mean, I'm aware of the change in temperature. Again, the question is how we can measure in the interface. It's a 8-inch cylinder of concrete. So
Had another seminar a couple of days ago. Japanese researchers who are technique for analysis. Quite frankly, I've never heard.
me neither.
Coating, very thin coat, and then actually changes based on. So.
Okay. Yeah, I'll touch base. That would be interesting. Yeah, yeah. Oh yeah, yeah, I would appreciate it. Yeah. Yeah.
Correct me if I'm wrong with this question. The frequency used testing was 1 or 1.5. Right?
Was 1.5 or 5?
So how does actually what frequency is there? Because it's gonna have a very significant effect on the
Yeah, absolutely. So there are different philosophies. So, but if you read the majority of the papers, they would say that in the application in bridges, the frequency usually doesn't go out of the range 1 to 10, with 5 being the most common. So that's where we stay, basically. Thank you.